Now, for the cases that the web tool doesn't cover, we've introduced a Python-based analysis library, and this is inspired by the Object Relational Mapping, or ORM pattern. This allows scripted analyses with comprehensive access to the data collected at runtime, whilst hiding complex post-processing steps. The general architecture involved with analysis scripts is that we start with a dataset from instrumentation and monitoring, just like with the web tool. We use an analysis API provided by the web tool, and then via HTTP and post-processing it into objects, we arrive at a point where we can do analysis using the library. In particular, this includes querying across the entire schema, performing path comparison and highlighting, and further call tree construction, which is not yet possible with the web tool. All of these features can be combined to do some sophisticated offline analyses, which include collecting data from multiple machines in order to detect whether the performance of one machine affects the performance of another that communicates with it. We'll now demonstrate how our Python library can be used in the Jupyter Notebook setting. So this is our first example of the VyPR analysis library being used to analyze performance data taken from a real-world system. In this case, it's our case study from the CMS experiment at CERN. And in this case, the service that we're analyzing is a service that takes data from runs of the Large Hadron Collider at CERN and uploads that data into a central database ready for certain activities to be undertaken by physicists. Now, the architecture of this system is distributed between a client-side and a server-side process. The client side proposes data to be inserted into a final database, and the server side receives the data and decides whether or not the data can correctly be inserted, whether any transformations can possibly be applied to the data so that it might be more appropriate for inclusion in the final database, and ultimately has to do all of these things within reasonable time. So we care about analyzing its performance in different ways. Okay, so the example that we show here includes trying to determine whether an optimization that we know will add a bit of extra time onto the process is actually effective enough to justify the extra time that we spend on it. In particular, when we send a lot of the data over the connection between the client side and the server side, we segment it into parts so that we can deal with an unstable network if we have to. But one of the problems is that quite often a lot of these segments of the data don't need to be uploaded, and if we were to upload them, we would take a lot of time and ultimately be wasting that time. So in this case, we care about trying to decide whether the optimization that we've employed to decide which bits of data should be sent is happening quick enough so that we can justify that extra time that's being spent on it. Because ultimately, if the optimization takes too long and it isn't really being that effective, then we may as well just turn it off. And in addition, we're interested in the cases in which we could turn it off versus the cases where we definitely know that we have to use it. So we start as normal with the analysis library by importing whatever things we need from the Python standard library as well as some other packages. But most importantly, we import the VyPR analysis library as you see here. We then take two steps. The first one is to prepare a dataset that we have, a local dataset, and this will have the effect of taking this database and starting up the central analysis server based on this dataset. We then set the directory of the local monitored service because we have the code locally, and this is needed in places where, for example, we want to do path comparison. So if you now run this part of the notebook, we see that we're setting up the server in the background using this database, and finally we've connected to the server, and now we output, just to be sure, the directory inside which the local monitored service is kept. Now our next step is to use a few of the functions provided by the analysis library in order to carry out our analysis. So the first thing that we do here on the first line is to get the list of functions, and we care about the first function. And the first function in this case is the function that carries out this hash checking optimization that you see here. Once we've got that function, we then get all of its calls that have been recorded by VyPR, and then from there we can begin to iterate through that list of calls and then perform our analysis in each case. So our analysis in this case consists of first getting the single verdict that was obtained, because in this case that we know from domain knowledge that there will only be one verdict because of the structure of the code. And then either we care about all of the failures or we care about them all. So in this case, for this analysis, we care about getting all of the data regardless of the verdict that it generated. So we say, okay, for each call of this function that took care of the what we call the hash checking optimization. Then first of all, we get the verdict that was generated by that call, and then for each verdict we get the observations, and the observations are just the measurements that were needed to check whether that verdict was true or false or not. For example, in the web tool that we saw earlier, in the specifications listed, in a mixed atom we might need 2 observations. So in this case you see that we get a list of observations, and then we take the left hand side observation and the right hand side observation. And in both cases we use a filter, and we care about, okay, the left hand side observations should have the subatom index 0, and the right hand side should have the subatom index 1. And in each case we just take the first thing that we find. So now we care about processing this data that was observed and extracting the important part of it, and this is what this part is for. I won't explain fully why that's needed because it doesn't really add to our explanation of the analysis library, but we can see here that we begin to build up a dictionary that maps hash lengths to how many were not found. The idea here is that for each number of hashes that we have, we maintain a list of all the hashes that were ever not found when that optimization was run for that number of hashes. So here, if I run this, then I'm going to fast forward through the analysis now, because this takes some time. Now, in particular, this is communicating with the server for every iteration, so this is actually quite a slow process. Now, future work and future plans involve trying to speed this up by reducing round trips to the server by, for example, just sending one request or just a couple of requests with all the information from all of the queries that happen inside this for loop, so that we can get all the data back in one go. So now that the analysis is finished, we can carry on to the next step of the notebook. And from here, I won't explain in depth what the code is doing because it's generally using other libraries and doesn't really show much of the analysis library being used. But this step is essentially going from the for loop that we saw earlier, from the map from numbers of hashes to numbers of hashes not found, and it converts these to percentages so that we can bin these percentages and put them into a plot. So if I run these steps, I run this, and then finally I run my plotting code, and this will ultimately, as you see here, yield a box plot. And you can see that while most of the times the percentage of hashes not found is actually quite high, so the optimization is doing a good job. But in this case, we can't see it here, but I can say that the hashes are always new. So out of the 4,000 function calls that we have, we see that of the ones that sent a lot of hashes between 300 and 2,000, which is easily the upper bound of the number of these hashes that we'd have to send, we see that a lot of them, or all of them in this case, actually result in all of the hashes not being found. So the final stage of the analysis is that we tear down the server, and if we run this, then the server will be stopped, and everything will be ready to do another analysis and run another notebook. Our second example of using the VyPR analysis library involves analyzing the behavior of some code with respect to a path taken. In fact, we'll analyze the same case as we showed in the web tool earlier when we analyzed the difference in performance between the two paths. But in this case, we'll do the exact same analysis, but using the analysis library. Now, the same as before, we start by importing the analysis library, as you can see here, and setting up a given dataset, and then setting the local path where the code is found that we're going to be analyzing. And then we include an extra input here, which is the machinery that is needed for path comparison and how it's implemented in VyPR. So we'll run this, and this will set up the database and start up a server in the background that wraps around this database and gives us the endpoints that we need to do the analysis using the analysis library. So most of the major logic in this is performed quite early on. So in this block you see that first of all we get the metadata function that we care about, then we get the property over that function that we care about, and we'll use this later to make sure that we get all the calls that are, all the verdicts rather, that are relevant to that property over that call. So in order to do path comparison, we also need to construct the symbolic control flow graph in memory of the relevant function. Now this requires that we've told the VyPR analysis library where to find the source code of the service that we're analyzing, because ultimately this source code will be read in and used to generate the symbolic control flow graph. So we generate the symbolic control flow graph here, and the next thing to do is derive a grammar. And as we saw before, we need a context-free grammar in order to do path comparison. So This step is part of that process. And the next thing that we do, along with, in agreement with what we did before, is to get the list of calls. And here you see that we look at the metadata function, the relevant function in the service that we care about, and get all of the calls of that function when we run it. And we then iterate through it, which is the same pattern that we used before. The one difference now is that when we get the verdicts for each of the call, now we care only about the verdicts that are relevant to a specific property. For example, if there are multiple properties being monitored over the same function, then the verdicts generated are different for each specification. So for each specification, I will get a new set of verdicts with respect to the observations generated for that particular specification. So I need to be precise when I get this data using the VyPR analysis library. But luckily, it's possible to filter this and to indicate which data you want precisely. So once I've got these verdicts, because there might be multiple, I iterate through them, and then I say, well, I only care about the verdicts with the binding equal to 3, and such that the verdicts were a violation. Then, once I've gotten this verdict, I get the observations that were required to reach that verdict. From here, the next thing that I want to do is, as we saw in the web tool, I want to measure the time taken along the different paths taken to get between point A and point B, where point A was a change to a variable and point B was a function call. So to do this, the VyPR analysis library provides some nice functions that make this very easy. So first of all, I want to get the path up to the observation that happened first. And to do this, I get the first observation and then call reconstruct reaching path along with the symbolic control flow graph that I constructed earlier. I then do the same for the right-hand side observation. So the left-hand side observation was the change of the variable that we saw, and then the right-hand side observation was the call to the function right at the end of the main function body. I then want to calculate the path difference, and so here I do this in quite a low-level way. I just treat the path as a list in Python, and I use Python's nice slicing syntax to be able to essentially subtract the path reaching the left-hand side observation from the path reaching the right-hand side observation, because ultimately the left-hand side path will be a subpath of the right-hand side path, because the right-hand side observation happened after the left-hand side observation in the same function call. The next thing that I do is set up a parse tree. And so earlier how we discussed that we need to construct the parse trees of the paths that we care about so that we can intersect them, this is what we do here. So we instantiate a new parse tree based on the path difference that we have. We're using the grammar, and then starting at the initial state of the first part of the path difference. Now this is a technicality and requires a little bit of knowledge of the underlying theory, and this is one of the reasons why the VyPR analysis library is more useful and more flexible, but requires a lot of knowledge of how things work underneath. So the next thing that we do once we've got the path is to get the timestamps measured on the left-hand side and the right-hand side, and then calculate the time taken. And we then add these pairs so that we have a correspondence between the parse tree and the time taken. And finally, we calculate the intersection, and this, as we saw before, will tell us where the paths diverged. For example, if we take our parse trees and then intersect them, we will find out which nodes or which vertices in those parse trees relate to divergence or disagreement of the subtrees of the parse trees. So if I then run this code, so once we've performed the intersection, what we will have in memory is a structure representing the paths, the intersection of the paths, along with any point of disagreement, so that further on in our analysis, we can access those points of disagreement, and for each of the paths that were involved in the intersection, we can determine what that individual path did in that case. So if we now look at the code that we use to figure out which path took which possible subpath through the region of disagreement, then we see that the first thing we do is to get all the path parameters from the intersection, and this will populate a list for us. And then when we iterate through the list of parse trees, we use the path parameters that we've derived and then use a method called readLeaves, and this will give us the subpath that was taken by each of the individual paths in the intersection through the region of disagreement. And based on this, we can divide up our performance data with respect to the path taken. So if I run this cell now, then the resulting structure in memory is a map from parameter value indices. In this case, we just have two parameter values, so we have a map from 0 and 1 to the times taken for each of those paths taken. And now finally we have the plotting code, so if I run this will generate a nice plot for us. And we can see that we now have two plots, each one corresponding to a different path taken through the code based on the analysis that we did in order to determine the possible ways in which paths could diverge. So as we see, we've roughly reproduced the plot that was given by the web tool, and in here obviously it required more work, but we saw that there's a lot more flexibility. So to conclude this tutorial, we have introduced the theoretical foundations and implementation of a framework for the performance analysis of Python programs. This has involved introducing 1. A new temporal logic for specification of source code level properties, 2. Instrumentation and monitoring approaches, and 3. An explanation approach. In a significant step towards making runtime verification a viable tool for software development processes, we've also introduced prototype tools for various kinds of analysis, including a web-based analysis environment and a Python library that enables software engineers to write sophisticated offline analysis scripts. But there is still plenty of room for improvement. In particular, we could develop more precise instrumentation approaches using data flow analysis. We could add features to the web-based analysis environment to remove dependence on the Python library. We could improve the expressiveness of control flow temporal logic while maintaining the trend of aiming for friendliness to engineers. And we will continue our work on integrating VyPR into software testing pipelines, which we've already begun in the context of continuous integration. Now that's it for this tutorial, and on behalf of the team, I would like to thank you very much for your time and encourage as many questions as you have.